One of the most important figures in Lindsay's third baseball paper is this one here, Table 1, which is the distributions of scores in remainder of the half inning that he studied. Now, he combines data from his original first paper in baseball, the 1959 paper, where he looked at bases loaded data from 1952, 56, 57, and 58. Those data from the first paper are included in this table, and they're right here. This is the data from the 1959 paper. Now, in addition to the 1959 data looking at bases loaded full, he collects data from all other base out situations, from 3,033 half innings from 1959, 176 different games, and from 3,366 half innings from 1960, 197 games. And that's included here. This represents the data from 1959-60. Those are the years that they're from. This column here are the base states. O means no men on base. I here means man on first, man on second, man on third, first and second, first and third, second and third, and this is full, just like he did in the earlier paper where the bases were full. So that's represented by the F here. Now what's also represented here, besides the base state, is the out state. He also represents the out state, 0 outs, 1 out, or 2 outs. So all the different 24 states of the game are represented in this table. And what he's plotting here are a couple things. He's plotting on this table here, he's plotting the number of times that situation occurred. The number of times in his data, looking at these two sets of games, 1959 and 1960, he looked at these sets of games, and every time a situation occurred with nobody on base and nobody out, he started recording it. That happened 61 times. And you can see all these other states occurred during those games he was looking at. So, for example, there were only 92 instances of bases loaded full, nobody out. In all the games he looked at, it happened 92 times. All the different base state situations that he analyzed are here. So only 92 out of about 27,000 times did he reach this state of outs, 0, and bases loaded, full bases. And so that's what this column represents, is the frequency that these situations occur. And that's an important column because that gives part of his value when he looks at the batting data. He looks at the situation that is in and the probability that that situation occurs. Then he looks at the probability with that, given that situation, the probability of scoring 0 runs in that situation for the rest of the inning. The probability in this column of scoring 1 run or 2 runs or more than 2 runs. This is what he represents in each of these 4 sets of probabilities. Each of these probabilities adds up to 1. And you can convince yourself of that by just adding up these 4 numbers. Once you do that, you'll see that it adds up to 1. So the probabilities here across this row add up to 1. So the complete set is probability of runs greater than 2, probability of 2 runs, probability of 1 run, and probability of 0 runs. Now the other thing to note, as the outs go from 0 to 1 to 2, just look at these numbers here. As the outs go from 0 to 1 to 2, it increases. You're getting an increasing probability of no runs scored. You're less likely to score runs as your offense makes more outs. And this makes complete sense that you change the probability of scoring runs, 0 runs upward as you make more outs. But again, all of these 4 sets of data add up to 1. One thing to note here is this column also. This column here is the expected runs given the bases and given the number of outs, the expected runs you're going to score. This is the average runs scored in that situation. So the average expected runs with nobody on base and 2 outs is .102. You're not expected to score many runs in that situation. But if you're in the situation, bases loaded, no outs, your average expected runs goes to 2.22 runs. Okay? Bases loaded, 2 outs, you're expected to score .823 runs. So if you look at the expected runs here that Lindsay demonstrates based on his half-inning observations, over 6,000 half-inning observations from these data, and then other sets of observations from these data, you'll see that it sort of makes sense. At the start of an inning, with nobody on, nobody out, you're expected to score .461 runs. And here's the standard error of all the different situations. Now, one other thing to note in this table is that you might want to start looking at these two sets of data and comparing them to see what they look like. Are they similar? Is this value here close to this value here? And if you look and compare these, they're about the same. Now, these are different data. They don't have to be precisely the same, but you can see that they're approximately the same, that there's not much difference in the probability of scoring 0, 1, 2, or greater than 2 runs across these probabilities, and also in the expected runs you get when the bases are full, nobody out, the bases are full, 1 out, and the bases are full, 2 outs. And they're about the same in both sets of data, the 59-60 data and the 52-56-58 data from the 1959 paper, which is what this section represents. So this is a very important table that Lindsay puts together, and what he's doing here is he's talking about the way to get value and also the way to analyze strategy in the game. The advisability of a baseball strategy can be looking at the changing game state. So if you're in this situation here, and you've got nobody on base and nobody out, but then that batter hits a triple, you transition to this situation here. There's a man on third and nobody out. And you transition from expecting to score .461 runs at the start before the triple, then after the triple, you're expected to score 1.39 runs after that. So there's an added expectation of runs, and you can ascribe that to the batter who just hit that triple. The other factor is you can say, when I look at all triples hit across all these situations, I can take the probability of being in that situation, which is represented by these two numbers here, the top numbers here, all represented here above this line here. Those top numbers would be in the numerator, and this number here, 27027, would go in the denominator to represent the likelihood of any of these situations. You can take the probability of being in any of these base out situations. Consider what happens if you hit a home run, a triple, a double, a single, and then you can see the change in this base state. You can say the triple goes from this state that you're in here to this new state, and we've changed the expected runs from here to here. Now, what if you make an out? You can go the other way and look at how outs change expected runs. Now, Lindsay doesn't look at the out case as much as he looks at the hit cases of singles, doubles, triples, and home runs. But he uses this data table that he creates of the distribution of scores in a half inning to better understand value and to also better understand baseball strategy. Would you want to intentionally walk someone? How does it change the base state? So, for example, you might be in this situation here. Man on second and third, 1 out. And the expectations is 1.56 runs. And if you're the defense, you're thinking, maybe I want to walk a batter to load the bases. Intentional walk here would go from second and third, 1 out, to bases loaded, 1 out. Well, you've changed your expectations to actually scoring more runs in that case. And that may not be the best strategy. The same thing with man on second and third, 0 outs. You actually increase the expectation of runs by doing that. So this is the kind of analysis on situation that Lindsay does. And he also ascribes this to the complete batting profile. What is the value of a single across all these states? What's the value of the double, the triple, and the home run? This is the start of linear weights thinking. A measure of batting effectiveness is developed here by Lindsay. Before it was slugging, batting average, RBI were the measures of batting effectiveness. But now he starts developing a new measure of batting effectiveness. So this new approach to batting effectiveness has 3 assumptions. There's 3 assumptions here. And let me just iterate them. The 3 assumptions here are, first, the purpose of the batter is to cause runs to score. So you want to measure how runs are potentially scored, how on average you improve your run expectation with batting performance. The second assumption that Lindsay talks about is that the measure of batting effectiveness of a player should not depend on the situation. It should be situation independent. You should measure the batting effectiveness across all situations and just understand the probability of being in that situation from this column here. This column here, again, gives you the probability of being in that situation. And you don't want to really use RBI at all for the measure of effectiveness of these things. And third, the probability of making different kinds of hits should be independent of the situation of the bases. In other words, not clutch. But Lindsay says most think that this idea of clutch exists. But his quote from the paper is that evidence on this point is difficult to secure. In other words, evidence for clutch behavior by batters is hard to find, according to Lindsay. So this is the basis of run expectancy. It's the basis that starts linear weights thinking that leads to Palmer's work, that leads to ideas like Tango's WOBA today, that leads to a value-added approach to measuring batting that sabermetricians have been developing since really Lindsay, but it started reoccurring in the 80s by Palmer and Skoog and many other sabermetricians. Very important table. This idea of linear weights thinking was started over 50 years ago.